welcome everyone. Welcome to my talk on forgetting factor for recursive least squares. My name is Ankit Goyal, and this is the work that I've done with Professor Dennis Bernstein at the University of Michigan. So many control and estimation problems, they minimize the quadratic cost function recursively to update the underlying controllers or the estimators. The minimizer theta k is computed recursively, and the matrix P of k accumulates the information that's coming from the data. So in all these, whenever you implement a recursive algorithm, these recursive algorithms needs to be started. That is, you need to select a value of theta naught, which is the initial minimizer, and the matrix P naught. Usually it's called the covariance matrix. Now, if you set the value of these matrices, if you set the value of the matrix P naught too high, the estimator or the controller becomes too aggressive. If it's a controller, it might end up blowing up the system. And if these values are too small, the estimator or the controller might be too slow. So to speed up the slower system, usually standard forgetting is used. Now, what the exponential forgetting is doing is that it's emphasizing the new data more and more, and it's forgetting the past data. So it reacts to the data as the data comes in. But if you keep on forgetting when no new information is coming through the signals, that's not really a smart thing to do, because you might end up forgetting basically just about everything. So recursive least squares, the least square problem, which is this is just the standard least square problem with the exponential forgetting captured by the scalar lambda, which is usually set between 0 and 1, very close to 1. So the minimizer of this cost function can be computed recursively using these two equations. Theta k is the minimizer of this function, this cost function j of k at the kth step, and pk is the pk is updated using this recursive equation. Now pk is actually equal to the inverse of r of k, where r of k is this equation. So this is really the information accumulation. Usually it's also called the information matrix. And this rk can actually be recursively written as this guy. And in fact, if you invert this using the matrix inversion lemma, you get back this. So this is the key idea. This is basically an observation over a lot of numerical experiments that I've been doing. So if you look at this update equation for the covariance matrix P of k, and we set lambda equals 1, so that is no forgetting. All the data is equally weighted. What we see is that pk is positive definite. It's very easy to see. It's not increasing. And when I say it's not increasing, I mean in the positive definite sense. And the observation is that all of the singular values of P of k are actually not increasing. And they will decrease based on the data P of k, the signals that you're getting. Now the main observation is this. So all of the singular values are not increasing, but only those singular values of P of k decrease that correspond to the singular vectors that contain new information. And I'll make this idea a little more concrete. Now, we have observed this in numerical examples many times, and I also show a small proof. Now, if you had forgetting, if you apply forgetting, that is, you set lambda equals less than 1, in the previous case, those directions which were not getting information, those singular values would just not change. But now, if you're not getting new information, those singular values keep on getting divided by lambda. And if you keep on dividing something by some number which is less than 1, that number is going to keep on going. And what ends up happening is that P of k eventually blows up. So that's what the goal is. I want to stop that from happening. So the information directions that I was talking about, let me make that idea clear. So I showed that the covariance matrix, which is updated using this equation. So what I do is I look at the covariance at the previous step. I use singular value decomposition to break it down as U sigma U transpose. And then I say the columns of U, which are the singular vectors of P of k minus 1, those are the information directions. And the corresponding singular values, which are contained in sigma, those are the information content held along those information directions. So what is the observation? The observation is that the new data which is coming in, phi of k, I can actually decompose that along the singular vectors which were available at the previous step. And that is quite easy to do because once you have the SVD, u of k minus 1 is an orthonormal matrix. So if I say that, so what I'm trying to do is I'm trying to decompose the new data phi of k along the columns of the along the singular vectors at the previous step. So I can write this equation, and then psi k is just going to be uk minus 1 transpose phi k because uk minus 1 is orthonormal. Let me try if this works. Yeah, so this is what. Yes. Oh. Okay, I don't know how to get the topic. Okay, so what I'm trying to do is, I'm trying to decompose phi k along the columns of uk minus 1. So entries of psi k, this psi k, they correspond to the information that is contained in phi k. Or equivalently, the columns of uk minus 1 along which phi k lies, they are the singular vectors along which I have new information. So in this cartoon you can see, which should run again, that the red phi actually, so the blue directions u1, u2, u3 are the columns of u, and the red, I'm showing phi in red, and it has components along all three directions. So I say that phi1 has information along all three directions. But whereas in the green phi, I only have information along u3 and u1. So those are my information directions. Next. So a little fact that I'll use to show an example. If you have a signal u of k, which is basically a sum of non-zero constant and a bunch of frequency, and then you construct this vector phi of k using the samples from this signal. This is an n-dimensional vector using m values of u of k, and this u of k contains p harmonics and one non-zero bias. Then if you construct this matrix, where k is much larger than m, then its rank is actually going to be one of these two numbers. So it's either going to be full rank, or it's going to be, or its rank is going to be decided by the number of frequencies that were carried in the signal u. This one is actually coming from the non-zero bias value. So if you see in this example picture, so red is my signal. It is composed of these three frequencies and a non-zero constant. And if I compute, if I take m equals 10 and compute this phi of k and construct that matrix for the entire data, the rank of that ends up being 7. And I checked it numerically, it works. So what does this mean in RLS? So we see that that matrix actually shows up in the RLS derivation equations. So what that means is that if my phi had those three frequencies, and I had m equals 10, then this rank will only be 6. Let's say that the non-zero constant was not there. And so this means that the data is actually constrained in a 6-dimensional subspace because this matrix rank is 6. So those corresponding 6 singular values will keep on decreasing. The last 4 singular values will not decrease. And in fact, if you do apply the exponential for getting, those 4 singular values will keep on increasing and they will eventually blow up. So this is a numerical example showing that conjecture. So let's say we try to fit a 5th order IR model to a system, to a linear system which is driven by 3 frequencies. So linear systems, sinusoids go in, sinusoids come out. So I have only 3 frequencies in the regressor vector that I'm going to be using to estimate the IR model. Since I'm trying to fit a 5th order model, so that means I have 10 parameters that I'm trying to estimate. And these two pictures show so this picture shows the covariance matrix that I get when I'm trying to estimate those 10 numbers. Now you can see that since I only had 3 frequencies, 1, 2, 3, 4, 5, and believe me, there is one which is still decreasing. So only 6 singular values are decreasing, other 4 are constants. Now, but when I do apply forgetting, this is what happens. Those 6 singular values, they converge because forgetting is forgetting, data is increasing the singular value. So they eventually, it's a trade-off. Eventually they will converge. But the ones which were not getting data, they keep on blowing up. And eventually MATLAB cannot handle the numerical computation of the singular values, and everything goes up. So this is the problem that we're trying to solve. So these are the problems that we see with standard forgetting. All directions may not carry new information, and this usually happens if the data doesn't have enough persistency in it, or you're trying to just overfit a larger model to the given data set. And this is extremely common in adaptive regulator algorithms. We see this all the time because eventually phi is going to converge. When phi is going to converge, it's going to have only constants, and that matrix is going to become rank 1. So this is what I propose. We propose targeted forgetting. We only want to target the forgetting to those singular values which are getting new information. I'm not sure what these things are, but anyways, so you saw that RK was lambda times RK minus 1 plus data. So I modify that as these two matrices. In fact, it's one matrix, and I pre-multiply and post-multiply. And the reason I'm pre-multiplying and post-multiplying by the same matrix is because I want to maintain the symmetric positive definite of RK. So what I do is, I take the RK minus 1, I decompose it using SVD. I write UK minus 1, sigma UK minus 1 transpose, lambdas just stay like that. And then I can decompose phi case and get psi case. So I can write this guy as this guy. And what I want to do is I want to apply forgetting to these sigma 1s, sigma 2s all the way to sigma n, depending on where I'm getting the information. So the problem is now UK minus 1 is there and lambda was outside. So I want to pull lambda 1, this lambda inside, and that can easily be done by this formula. So I can write it always, I can always find lambda k bar instead of lambda k. And in fact, lambda k bar is what I would choose. I'm selectively going to apply forgetting to these singular values. And the way I'm going to do it is that if that component of psi k, if the component of psi k is larger than a threshold, I forget. If it's smaller than a threshold, I don't forget. And then I back out the value of lambda k that needs to be applied in this expression using this simple formula. I'm just equating these two equations, and since UK minus 1 is orthonormal, I can move it left or right. So the equations end up looking very much like the standard forgetting. This is the way PK is just defined to be the inverse of R of K, and I use the matrix inversion lemma to get a very similar looking equation, but instead of PK minus 1, I have PK minus 1 bar, and PK minus 1 bar is defined as this guy, where lambda K can be computed using these steps. It's just simple algebra. So I showed you that with standard forgetting, those 4 singular values blew up. Now with targeted forgetting, those 4 singular values actually do not blow up, because I'm not applying forgetting to those 4 singular values which are not getting information. So that's it. That's what we do. And what if we had noisy data? Noisy data actually helps standard forgetting, because in that case, P of K is going to be the data that you're going to have. It's going to have information contained in every direction, but the noise is not going to have the same information that your actual data has. So eventually it does converge, but look at the numbers, 10 to the 10, right? That actually signifies the level of the noise. And so I set that cutoff point at which I am deciding not to forget to be lower than the noise levels, and hence nothing actually affects the targeted forgetting factor. So the targeted forgetting actually works the same way with or without noise. You just have to choose the cutoff point a little carefully. So a little example which shows this in practice. I'm trying to estimate these 4 numbers in a second order linear system, and then I say that for a long time, the input is just not going to be exciting, persistently exciting. If if I drive it with a step, that's not an exciting input. So if I did standard forgetting, my parameters try to converge in the first 10,000 steps. During this point, during this period, the input is not sufficiently exciting, which means, well, let me say it the right way. So during this period, the input is not exciting. It's only a step. It's only producing a constant number. Many second-order systems produce the same step response. So the system just converges to some system which produces the same value, and you see that the error actually does go to 0, even though the parameter error has stabilized. Now, because I'm using standard forgetting, P is blowing up. As soon as the persistency comes back in, you have a tiny error and a huge P matrix, which is like a gain in the estimator. It just blows up the parameter estimate. Eventually, least squares, because of the properties of least squares, everything comes back, error goes to 0. Eventually, it will converge as long as the data is persistently exciting. But how does targeted forgetting work here? So for this part, for the first 10,000 steps, we see the same behavior. For the next 50,000 steps, when the data is not sufficiently exciting, you see the same behavior. It converges to a system which produces the same step response. Error goes to 0. Delta theta converges to a constant point. But the singular value of the P matrix do not blow up. They remain well behaved. And when we get back the persistency, nothing happens. We eventually go back to the correct value of theta. The theta converges to the right values. Error again goes back to 0. So that is it. Yeah, we presented this novel approach to apply target forgetting in the covariance update. And this is based on the idea of these information carrying directions. Now, the bad side, because nothing is free in life, is that this approach is quite expensive, but it's still useful in estimation problems. Because estimation problems, you can just sit around and let it estimate. And that is it. Thank you so much for coming.
Any questions?
Question.
Okay, please.
Yeah. Could you go back to the example definition?
Yes.
Because you are assuming the constant parameters for the model you are estimating.
Yes.
But then you are using the least squares with exponential forgetting.
Yes.
Why is that? Because you can use the ordinary least squares without forgetting because the parameters are constant.
This example is just chosen to demonstrate the problems with standard forgetting. So I'm basically cheating and using bad points to show how bad standard forgetting is. Really, my focus is to show that some things can go wrong with standard forgetting. In fact, we apply this technique to other problems, the other algorithms. And those other algorithms actually use a quadratic cost function. And in those algorithms, so in that particular estimation problem that I'm dealing with in my work, that absolutely needs forgetting. And I used to see that whenever I reduce forgetting, the system would just blow up before actually giving me good estimates. So yeah, I can solve this problem very easily, but I chose this example to demonstrate that standard forgetting can actually do bad things.
Yeah, and maybe one more just comment. You have to set up the lambda, like the forgetting coefficient, and you have to set up the threshold, the E or epsilon. So any recommendation, are those constants somehow related, or you have to, or you can set up independently of each other?
So this one.
All right.
So this one, this usually, so if you're doing an estimation with noisy data, this can be guided by the information on the noise levels that you have. So if your noise level is like SNR, so if your signals are of the magnitude 1 or 10 and your noise is 10 to the minus 4, then you can say that any singular value which is less than 10 to the minus 4, that is basically corresponding to noise. So I don't want to forget that part. So you can set this epsilon based on that information, and lambda that I'm applying. So I'm applying lambda to only those singular values which are getting new information. So that's basically speeding up the algorithm. So the smaller it is, more adaptive your algorithm.
So, very quick question.
So recursive algorithms have a Kalman filter equivalent, right?
Yeah. So effectively,
So what is now the modification that you will make to the Kalman filter?
yeah, that is something. So I presented this work a few days back.
And in
also.
fact, probably there you'll be able to answer the noise part much better because you can separate out measurement noise from process noise.
Yeah. I have to think about that. I haven't thought
It'll be very
much.
interesting.
Yeah, it would be interesting. Yeah, thank you. I'll keep that in mind.
Sure.
Yeah. Do I have time for one question?
Thank you for that. I think if we do know the signal to noise ratio beforehand, which is very common in practice, so how do you choose the ratio?
So that would guide your choice of epsilon.
But that requires the knowledge about the signal to noise ratio somehow.
Yeah.
Yeah,
that
You'll have to do it iteratively.
Right. Or I mean, one way to do it is do it multiple times, and you can get an idea of what the